Good afternoon and welcome to MAE 106, Discrete Mathematics with Probability. My name is Richard Kohar, and yes, I will get those. I am getting back to those PDFs. They're taking me some time to scan. Thank you. Yes, exactly. I appreciate that. And thank you for holding in for the technical difficulty that we're trying to connect through YouTube. So, just as we were talking about a question yesterday, last class, and the question was how many three-digit numbers exist such that the digits sum to 5, and what I could come up with just using our kind of just simple counting techniques is to work through it this way, just using a tree diagram. So in total, working with the digits, you have for the first digit, okay. Yes. I have 1, 2, 3, 4, 5, excluding 0, because I don't need that for the first digit, and then you can work it out this way. In total, that there is 15 three-digit numbers that sum to 5, and is there a quicker way? We might come up with something a little bit later. So, let's start off with our lecture. We'll do a couple more exercises in permutations, and then we'll introduce the idea of combinations, which are arrangements where the order does not matter. But with permutations, these are arrangements of objects in which the order does matter. So, here's lecture 18. Will you be posting? Yes. Yes. Okay, and if the screen is blurry, just check to see if the resolution has dropped. So sometimes if your connection isn't the best, what YouTube will do is they'll drop you down to like 480, 360. Exactly. Make sure you check your buffering and resolution rate. Perfect. Thanks for everyone for helping them out in the chat. Okay, so this is an example from the textbook. So we have a president and a treasurer. This is kind of like a very typical permutations problem that you'll see. And we have a president and a treasurer are to be chosen for the RMC Flying Club. There's 50 officers in the club. Only one person can hold a position, and that is a person cannot be both the president and the treasurer. How many different choices of officers are possible if... So for part A, so let's use what is called direct reasoning or direct counting. And direct reasoning is where we actually count the things that we want, right? And then the indirect is where we count everything and remove the stuff that we don't want. So the total number of officers, or the total number of choices of the officers, if there's no restrictions, then we can think of it as we have 50 choices, and we're going to choose 2. Or, sorry, we're going to permute 2. And using our formula, that could be written out as, remember, when we have n permute r. That's n factorial over n minus r factorial. So that's 50 minus 2, which gives me 50 factorial over 48. Or I can expand that out just a touch so that I have the 48 there. I can cancel that out. Which is nice because this is what we kind of expect, that this would be the number of choices for the president. So that would be your first selection. And then, so the times is the and then you pick the treasurer. And so I should be showing that I can do this by hand. Let's do this times 5. 9 times 5 is 45. 4 times 5 is 24. So that'll be 2,450. Okay, so again, kind of just picking this. So we have 50 officers. These are kind of things that we're looking for and are important. And we're picking a treasurer and a president. How many different choices of officers are possible? What's the next one? Okay, so some people might get hung up. A, B, C, D, E. These are just generic placeholder names for people. So maybe on the test they'll have a name or whatever, but the idea is that it's just a person. So let's see. For this one, it says A will serve only if she is president. So how many ways is that possible? So what we can do is we can do direct reasoning as well. And, okay, so for this one, so in this, we have two cases. We have it where A is president, and the other case is where A is not president. So that means that for the first choice, for the president, for A to be selected, there's only one. And then, so that's the multiplication principle, and we'll have the treasurer. And for this, there would be 49. So that means that there's 49 cases, or sorry, 49 choices for this first case. Okay, and then for this second case, A is not president. Well, for this, that means that I would have 49 choices for the president. After I pick that, then treasurer. How many choices do I have for treasurer? I'm just going to wait for some in the chat. 48. 48, yes. Yes, 48. I was wondering if some people would say 49 because of putting A back in as part of the treasurer. But if we look back, it says again, A will only serve if she's president. So she won't. This also means that and not as treasurer. So then that means it's 48. Or we can think of that as 49 permute 2. Is contrapositive is indirect counting. Yes, contrapositive is called an indirect proof. 52. Okay, so then in the total, so therefore, the total number of ways is, so we would do 49 plus 2,352, which works out to 2,401. A is too good for that. Okay. So we have that one. Okay, so we did A, B. Let's do number, here's page 2. Okay, so for C, no, we have a click. B and C will serve together or not at all. Okay. So again, we're going to do direct reasoning. Okay. So there's two cases again. We have the first case where they serve together. So B and C. They're together. And how many ways can B and C be together then? Okay, so I got different answers from different people. I have 1 and 2. I have 2, 2, 1. Okay, so over here, I'll just think of this as here's my president. Here's the treasurer. So let's see, if I pull out, here's for black, let's use B for black and C for, here's cyan. So I can have B and C for treasurer, or I could also have C as president and B as treasurer. So just from that, there's two choices for president times, and then I'll have, here's the treasurer. Then there would be one left over. So that means that there's two ways. Okay, so then we have to figure out the number of selections when B and C are not chosen. So they're not selected. So for that, so we would have, so again, we had 50 officers. We're not going to pick B or C, so that means that we have only 48 to pick for president. And then from that, I would pick one, and I would have 47 to choose from for the treasurer. Okay. So that's, again, that could be written out as 40H permute 2. 48 times 47. 2,256. Oops, and I'm writing it off the page there. So, maybe I'll push it up just a touch. There we go. So therefore, so it's 2 plus 2,256. So that's just 2258. Perfect. Okay, and then the last one that we have is D and E will not serve together. So this is D and E will not serve together. Okay, so the quickest way I can think about this is the indirect way. Indirect reasoning. So, like, direct reasoning, again, is like ordering the pizza the way that you want it. Indirect reasoning is somebody else ordered the pizza and you're picking off the toppings you don't want. So, the total number of ways is 50 permute 2, which we had calculated in part A. So we know that's 2,000. Everything except lettuce, yes. 2,450, exactly. Everything except the lettuce. We found that in part A. Not the ways we want. So we're going to subtract. So the ways for this, so the ones that we don't serve, well, that would be with D and E. Again, thinking about if I think of these as D and E, this is treasurer, or sorry, this is president and this is the treasurer. And then the other way is if this is president and this is the treasurer, so there's two ways. Which means then you just have the 2450 minus the 2 leaves you with 2448 ways that D and E will not serve together. Okay. There we go. And we finished the question. So that's the end of that example. Let's flip this over. Okay, so here's an example. This is, say, from exercise. And what I'm going to do is 4.2, and this will be, say, E. And so this one says solve for n. And so in this case I have is n factorial over n minus 1 factorial is equal to 7. So the way that we could solve this is I'm going to try to isolate for n. So let's do 7 times, and then I'm going to bring the n minus 1 over here. Factorial. Here's n. Well, here's n minus 1. Is this helpful or not? There's something that didn't quite work out. What can we do instead? Well, when we're stuck with something like this, we can try doing just small examples. So if I go over here and I'm thinking, let's say I have n factorial over 1 less. So then I would have, let's try something simple like 3 factorial over, and in this case, this would be 2 minus 1 factorial. So that would be 3 minus 1, which would be 2 factorial. So we see that it would be 3 times 2 factorial over 2 factorial. That cancels, and then I'm left with just 3. So we can do the same idea over here. I can do n times n minus 1 factorial all over n minus 1 factorial. We know that that cancels. And then I'm just left with n. But then that means that n is equal to 7. In this case. Is everyone okay with that? Excuse me. Can you prove it through substitution? Sure. So as a check, I can do 7 factorial over 7 minus 1, which is 6 factorial. 7 times 6 factorial, which equals 7. Okay. Now this is something that we call circular permutations. So it kind of goes along the lines of 6 people are invited to a dinner party and they're seated around a circular table. So there's 6 people. So they're seated around a circular table. How many permutations are there? Okay, so we wish to count the number of circular permutations, or the number of ways to seat these 6 guests around a table. And since the dinner guests are seated in a circle, there will be some duplication. So let's see. I'll draw this out. Let's say so here's 1. Let's see, I'll put 2, 3, 4, 5, and here's 6. So some people are saying 30. That's a good guess. I don't know yet. I have to work through this. So we have 6 places. So let me that did not work out as planned. Let's see. Okay. So there's an orange, there's a yellow. That's not very helpful. I thought they would give me different colors. Here's a brown one. A very malformed green one. Oh, well. And let's go with, we'll have a red. 5, and let's do color one with a marker. I wish I had the markers that worked on them, but they don't. So let's see. Oh yes, and let's do blue. So there's 6. So what we have a problem is that, for example, if I have, here's one here, here's another one there, we'll put that one there, and here's the brown one, there's the red one. And so basically the problem that we have is that, okay, here's 1, 2, 3, 4, 5, 6, that basically if they move down 1, let's say here, they move down 1, essentially it's the same arrangement, because all I have to do is just rotate it back into position like this, and now I'm back to the same ordering that I had previously. So this is the problem that we have. So any circular permutation can be rotated so that this first one, the orange one, what we're going to do is we'll fix that one. We'll fix this orange one, and then that will keep all our permutations. So that is it. So again, so I will always have this orange one in place, and then I can pick from the remaining other ones, the remaining 5, to do whatever I want. So again, so for instance, if you fix one of them, and by fix I mean like you stick or you glue one person in place. Which means then that for this seat right here, I have 5 that I can pick from. So I could say there's 5 choices for this. I'm waiting for my kids to get me more options. Okay, so then as I move to the next one, or I could pick this one, it doesn't matter, but I'm just going to move clockwise. Then as I move over to this one, I have 4 left over, so I'll pick yellow for this in this case. So there would be 4 choices. And then for this one, I would have 3, so let's pick the red cap here. 3 choices. I will pick blue. So there would be, say, 2 choices for this. So let's pick one right there. And I would have 1 left over there. Okay. Let's move that out of the way. So what we've done basically is, we fix 1, and then we kind of count our choices around here. So we had 5, 4, 3, 2, 1. So basically what ends up happening is that I have, for this chair right here, I'll have 5 choices, and then I pick the next one, which is then I have 4 choices, and then for this one I have 3, and then for this one I have 2, and lastly for this seat I have 1. So that is 5 factorial. So that's 5 times 4 is 20. So 20 times 3 times 2 is 6. So 20 or 2 times 6 is, sorry, here's 20. Here's 6. 2 times 6 is 12. So adding that 0 gives me the 120. So that means there are 120 different ways of placing the 6 people around the table. And if you want to generalize that, if there were n people sitting around a circular table, then there would be n minus 1 factorial arrangements. They are, but it is times 1. Is the fixed person not counted at all? They are counted, except that you can think of it as times 1. Yes, exactly. So you could think of it as just times 1. So there's that fixed person. Nobody was glued to a chair. Well, yes. Just to make sure that people understand what I mean by fixing, like affixing, or just kind of it's a standard term in mathematics that we use, and sometimes people might not understand what we're saying. So again, we're just kind of picking one and just setting it there. Okay. Right there. Yes, they're a human anchor for the table. So then, you know, extending that, if there was 7 people around a table, then there's 6 factorial, which is 6 times 5 factorial, or 6 times 120. And so that should be 720, right? Perfect. Yes, so there's never an option for anyone else to sit there, yes. Yep, and the reason for that, again, was because if we rotate it, it's basically the same seating or arrangement, right? So if I had this one here and this one, again, just as we had explained previously. Oh, and I had put the one cap away. You know, just moving down by 1. Okay, so I did that. I shifted it, but all I have to do is just rotate it back, and now I'm back to the same seating arrangement. So it's just that rotation that we are dealing with. Okay. So you can, there's kind of several examples, like 5 players on a basketball team, and how many ways can they form a ring around their coach? If you had 20 unique beads, how many different necklaces can you make? What is the minimum number of beads required to ensure that there's 24 different possible necklaces, and so on and so forth. Okay. So I have candy in the way. Start with page 4. So now we can also have permutations with repetition. So permutations with repetition, that means that I can have repeated objects. So instead of having, say, only one kind of each, instead now I can actually have repeated copies of them. So for instance, what I could do is I have, let's see. So I can have multiple copies. So what I'm going to do is, let's work with passwords instead. So here's just the example. Let's use passwords. Okay. So let's say that this is an old style password. It has 8 upper case letters. Oops. So it's only 8 uppercase letters. How many passwords are possible? So again, 8 uppercase. Oh, uppercase. There would be 26 of those. So that means that for the first letter, there would be 26 choices for that one. And then for the second, there would be 26 letters again. You would have 26 letters to choose for the third one, times 26 for the fourth one. And for the last one, we have the 8th. There's 26. So I'm not going to write out for the 5th one, the 6th one, 7th one. So that's 26 times 8 times. So I can write that quickly as 26 to the 8th. And that's quite a large number. So 26 to the 8th. So 208,827,064,576 ways. Yes, there's somebody's asking no calculators. But, so before people start panicking, this is an acceptable answer on the test. Acceptable on a test. This kind of gives you just an idea of how big or how many passwords are possible with just that is the best news of the class. When can we expect the next test to be? Not this week. I have a feeling that either the 5th of November or maybe not this week. No. Yeah, no, not a test this week. No. I would give you enough, and not tomorrow. Yeah. No, I will give you a warning. No, not necessarily a warning. I will give you heads up. Okay. So you have something like that. So in general, just in general, if objects are to be repeatedly selected, then the number of permutations of n distinct objects taken r at a time it's just simply n to the r. Okay. So this is what we need. So just using our example up here, in this case, we had n was equal to 26. So there was 26 distinct objects, and we were going to pick them 8 times. So 8 at a time. So r was equal to 8. So then n to the r was equal to 26 to the 8th. Okay, so here's an example. So if a light switch can be on or off, so it's not one of those dimmable ones, and there are 6 switches on the wall, what is the number of different configurations? So like there's 6 switches, and they can be on or off. 1, 2, 3, 4, 5, 6. So they're like little switches. So these are light switches. They're on or off. How many ways? The light's on and off. Somebody's writing 6 squared, 36, 12 factorial. Whoa, 12 factorial, okay. I like the fact that it's like exclamation point question mark, like 12? Like, got 2 to the 6. I was kidding. Okay, so I think I see a good answer. For the first switch, there's 2 choices, right? It can be either on or off. So there's 2. There's on or off. So there's 2 for the first switch. For the second switch, there's, again, on or off. For the third one, times 2. So you can kind of see where I'm going with this. So for the 6th one, again, it's 2. So that means that it's 2 to the 6th. And so if we remember counting by 2s, 2, 4, 8, 16, 32, 64. So there's 64 ways that we can turn off the different light switches. Perfect. So there was 6 light switches. 2 to the 6 is 64. Perfect, excellent. Okay, now we can start to move into combinations. Combinations. So these, again, are arrangements where the order does not matter. So for example, I could be thinking of a set, and let's say I have 1, 2, 3, 4, 5, 6, and from that, let's say I pick three of the elements. So if I did 1, 2, 3, now this is a subset of this bigger one up here. But we also know that if I write 3, 2, 1, that's the same set because they have the same elements. So it doesn't really matter what the order is. This is still equal to one another. And did I get all the... did I get all the sets in there? 1, 2, 3, 3, 2, 1, 2, 3, 1, 2, 1, 3. There's quite, oh yes, 3, 2, 1. But this is quite 1, 3, 1, 3, 2. Yeah, so there's 3, right? So how many different orders can I have it? There's 3 times 2, which should be 6. So 1, 2, 3, 4, 5, 6. Good. So there's 6 of those. So these are permutations, but this is just really one set. So this is considered one combination, but really there's 6 permutations. Okay, just to kind of illustrate the difference. So again, one combination, it doesn't matter what order that they're in, as long as it's 1, 2, as long as there's the elements 1, 2, 3 in it, and if there's the order that matters. So order matters, and over here this is order does not matter. Okay. So it would be nice to kind of figure out how many different combinations we can do. So this is kind of our motivating problem. How many Lotto 649 tickets are there? So if you're not aware about 649, or Lotto 649 is a lottery in Ontario here, where there's 49 numbers. One, two, all the way up to 49. And then you pick 6. So with a lottery ticket, none of the numbers repeat, and the order does not matter. And since the order doesn't matter, it's a convention to write the numbers in ascending order. So, you know, the order does not matter. But by convention, it is written in ascending order. Okay. And so this kind of selection of elements from a set, like 1 through 49, where the order doesn't matter, is called a combination. Yes. Okay. And so there's a long history of lotteries. Governments have been using lotteries to raise revenue without imposing additional taxes on people for expensive projects. So I believe the first national sanctioned lottery was by Queen Elizabeth I, and she was using it to raise funds for a crumbling building that was used to raise funds. And even for us here locally, in the 20th century, Montreal and Australia used lotteries to partially finance the 1976 Olympics. And so for us, that's kind of important because in 1976, Kingston also hosted the sailing competition here for the Olympics. So they kind of have played an important role in history. So here's a definition. We'll call it the binomial coefficient. And what we usually write this as, we'll write this as n, and here is r. And what this is that it's the number of ways. So what we can say is we have n objects, and over here we're going to pick r out of n. So these are n objects, they're distinct. And this again then represents the number of ways of picking r many objects from n many objects where the order does not matter. So we often then kind of just read this. Oops. So this is n choose r. Okay. So you might be asking me now, what is the value of n choose r? And at the moment we don't know, but we're going to be able to figure this out. So just using this definition, just kind of expressing it as this. For the lottery, for the lotto, there's 49 numbers, and you're going to choose 6 of them. So you can write that as that, or in words, that's 49, and we're going to choose 6. Now, what does that equal? We don't know yet. So we've introduced some notation for this problem. And again, we've identified what the unknown is. And this unknown is this 49 choose 6. And by our intuition, it's quite a large number. Otherwise, it would not have been possible for so many to play the lottery and not win. Okay. Now, with so many possibilities for a lottery ticket, it's unlikely that we can just list or write all of them out. So what we're going to do is we're going to find something similar. This is one of those problem-solving techniques that we use in math. And what we're going to do is we're going to recall one of those problems that we had done previously. Here's 6. And so what we're going to do is we're going to look at the example of 5 students lining up for a photo. Okay, so we knew. So here's like kind of here's our solution. Here's our solution, which was for the first position, we would have 5. For the second position, we would have 4 students left. For the third position, we would have 3, 2, for the fourth. And for the fifth one, we would have the remaining student there. Okay, so that's 5 factorial, or 120. Okay, so that's great. So let's say that you had the photographer. The photographer had all 5 students show up at once, and he was able to, again, line them all up. There's 5 factorial different ways, but we can think of it in a different way. So instead of supposing that all 5 showed up, suppose only 3 did. Okay, and the photographer has to get them ready because they're running on a tight schedule. And so the number of ways that 3 students can be selected from the 5 original students is denoted by, well, okay, so how many ways can we do that? Well, we can use, first of all, we need to pick how many those were. And we don't really care. So let's say, using this notation here, how many ways can we pick? Well, we have 5 students, and from that we're going to choose 3. So that's 5 students, choose 3 of them. Okay, we're fine with that. So we have this. That's kind of our first step. And then So we've got 5 students, we choose 3 of them, and then with those 3 students, we can start lining them up. So we can have 3 choices for the first student, and then for the second one, it's times 2. And then for that third student that showed up, just 1. So by the multiplication principle, what I did is there's 5 students, and we're going to choose 3 of them. 3 of them showed up, and then we're going to arrange them. There was 3 factorial ways, so times 3 factorial. Okay. So that's kind of the first step. Okay, then the other 2 students show up. Okay, which means that there was 5 minus 3 factorial, or you could think of that as 2 factorial, or you have 2 choices for that 4th place, and then you had 1 left over for that 5th place. So that's 2. So combining the whole story, by the multiplication principle, what we had was that we had 3 students initially show up, so we choose 3 of them, and we line those up, which was 3 factorial. And then, so that was for part A. And then for part B, we had the 2 factorial. Which is great. Okay, so we have 5 choose 3 times 3 factorial times 2 factorial. Now, you're probably thinking, but what is the number? Like, what's the actual number? So what's nice is that since we got solution 1 and solution 2, they're equivalent ways of thinking about the same problem. So they're different ways of counting the same objects. And therefore must be equivalent. Okay, so that means solution 1 and solution 2. So what I can actually do is I know that it's 5 factorial. So I know from solution 1, this is 5 factorial is equal to combining what we had from the solution 2. So this is from solution 1. Over here is solution 2. And it's this term right here that we don't know. So what I can actually do is I can solve for that. So I have 5, choose 3, and I have 5 factorial on the left-hand side. And I can bring over the 3 factorial. This is multiplied by 3 factorial times 2 factorial. And I can just bring that and divide it by it. So I have 3 factorial divided by, and also 2 factorial. And that's it right there. So let me just rewrite that out again. Here's number 7. Is equal to 5 over 3 factorial, 2 factorial. So we can solve this. 5 times 4 times 3 factorial. That cancels. And so I have 5 times 4 is 20 divided by 2 times 1, which is the 2 factorial. So that's just 10. Okay, so I want to make sure I check this. For solution 2, it was 5 choose 3 times 3 factorial times 2 factorial, which is then equal to 10 times 3 times 2 is 6 times 2, which is 12. 12 times 10 is 120, which is equal to 5 factorial, which is the solution 1. Okay. So now we did it for this one simple, small little problem, which was for 5 students lining up for a photo. But we're still, our motivating problem, which was, okay, we want 49, choose 6. And, okay, we solved it for 5, choose 3, which is 10. What we need to do then is, can we abstract this? Can we come up with a general formula? And the answer is yes. What we've done is we've got a very simple problem that we've done. And what we'll do is, instead of using the numbers like this, what we'll do is we'll start to set this up more generically. Okay, so I have, here's number 8. So what I was saying was that we had 5 choose 3 is equal to 10. Can we find a formula for n choose r? So what we're going to do is we do the same idea. So instead of 5 students, what we'll say is we'll have n students lining up. Okay, which means then that we can do our first solution, which was n times n minus 1 times n minus 2 dot 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 all the way to 2 times 1, which we know then is equal to n factorial. So that's the first one, so that's okay what we've done there. So what I'm doing is I'm just using my small concrete problem that I had done previously, and I'm just making it arbitrary now. Okay, so here's solution 2. Let's say, suppose only R students initially showed up. So instead of 3, we're going to call that R. So okay, so that means not 5 choose 3, but we're going to have n students and R show up initially. So there's n students, and we choose our mini. Okay, so that's okay. So with the R students, that's R times R minus 1 times dot 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 all the way to the 2 times 1, which then is just R factorial. So again, just following what I had previous up here. So again, combining this together. By the multiplication principle, what I have then is n choose R times R factorial. Okay? Just following what I had done in the previous one. Okay, for part B, so I had R many show up initially, and then I'm going to have the remaining students show up. So I have the remaining, so n minus R students show up. Which means that I have n minus R factorial ways to line up those other ones. So in this case, it would be, yeah, to line them up. So what we do is we combining A and part B. So the first group showed up, and then we arranged the second group when they showed up by the multiplication principle, because we're doing A and then B. What we get is n choose R times R factorial times n minus r factorial. Okay. Solution 1 and 2 are equivalent ways of counting the same objects So what I get then is for solution 1, I have n factorial is equal to my second solution. So this is solution 1. And on the right-hand side, I have n choose r times n minus r. So that's what we get for the second solution. So solving for n choose r, what I can do is I got n choose r, I have n factorial over bringing the r factorial and the n minus r factorial over to the left-hand side, goes down into the denominator, so that I'm left with r factorial times n minus r factorial. And there is our formula. So I'm just going to write that out again. Number 9, page 9. I'll make sure that I do it right in the, yes. So that's n choose r. And that's the number of ways that I can, from n distinct objects, I can choose r many of them. So going back to our lottery problem, which was the whole point we had 49 numbers. We're going to choose 6 of them. Using our formula that we have come up with, it's 49 factorial over 6 factorial, and then it's 49 minus 6, which is 43. This is still quite a large number because I have 49 times 48. So this is quite a large number, and you can keep simplifying it. But what I can do is I can tell you, and this is from a calculator, the number of possible lottery tickets is 13,983,816. Okay, so what's kind of different than what you might have seen in previous courses or in high school, what we have done here is we have done a combinational proof, a combinatorial proof. And so a combinatorial proof is a mathematical proof or demonstration that uses a situation or story about counting objects to convince you that the statement's true. So what we're doing is to demonstrate a combinatorial identity or formula. What we do is we do this by counting the number of objects in two different ways, and then we conclude by setting the answers equal to one another to obtain the desired identity. So what we've done here is, when we were working with here, with just the n students showing up, we counted it in one way, and then we counted it in a different way, but we're using the same objects. And because we're counting the same objects, and we can then conclude that we could set them equal to one another. And we can then come up with proofs. So again, we had counted it one way, and then we counted it another way. These are equivalent ways of counting the same objects. So what was good about this was we knew n factorial, we knew r factorial, we knew n minus r factorial. We can calculate these. You know, if you tell me what n and n minus the r is, I can calculate those quantities, but it was the n choose r that we didn't know. So that's why then we were able to solve for this algebraically. And solving for that algebraically, n choose r was n factorial, and then bringing over the r factorial and the n minus r factorial into the denominator. So again, that's n choose r. And so that's derived by a combinatorial proof. So you can think of it as a story of counting objects in two different ways. And this simple technique is powerful enough to prove many identities and results in combinatorics, which is that branch of mathematics that we've been kind of walking and taking a tour through. It has the advantage of being elegant, short, and intuitive over kind of an algebraic approach. Okay. So Okay, it's more intuitive. I'll give you an example. So here is this is called the symmetry of combinations. And what that is we can do n choose r is equal to n choose n minus r. So here's the algebraic proof. What we're going to do is I'll start with the right-hand side. So n choose n minus r. And using the formula, right over here, I'll just kind of write that n choose r is equal to n factorial over r factorial n minus r factorial. Okay. So that means that in the numerator, I'll have n factorial. And then I have r, but in this case, it's n minus r, so it's n minus r factorial. And then I'm going to just write some square brackets because I need to do n minus r, and in this case, r is n minus r. So I have n minus n plus r. That cancels. I'm left with n factorial over n minus r. I'm just going to write this here, just exchanging it. So I can do that by the commutativity of multiplication. So again, now I have it matching the same over there. So that's equal to n choose r. And so we're done. Okay. Here is the combinatorial proof. So what I'm going to do is count it on one side. So on the left-hand side, I have n apples, and I pick r many. So that is n choose r. So that's the left-hand side. the right-hand side. So again, I'm coming up with some sort of story. So I have n apples and I pick R many of them. That's good. And choose R. For the right-hand side, again, I have n apples and I don't pick or select n minus R many. So that means that I have n choose n minus R. So that's what we mean by the symmetry. That if you say I have n many apples, let's say if I have 1, 2, 3, 4, 5. So in this case, I have 5 of them, and I pick 3. So let's say I pick 3 here. Well, what this is saying is that that is also equivalent to me picking, so I had 5 and not picking 2 of them. But this is the combinatorial proof, which for some people may be a little bit more intuitive. It's kind of nicer than having to rely on an algebraic proof. But you can see that the symmetry is, one way I can pick them is picking R many, or the other way is to not pick n minus R of them. And to show you this, I have 5 factorial over 3 factorial, 5 minus 2. And over here I have 5 factorial over 2 factorial, 5 minus 2. Oh, sorry. That should be 3. So 5 minus 3 is 2. And if I, so you can already see that the denominators are the same on both sides. I have 3 factorial, 2 factorial, but again, I can change the order because of multiplication. So I'm left with 20 over 2, which is 10. And same thing on this side. And perfect. So yes, that should be 5 minus 3. Okay, so thank you everyone for tuning in, and I will post these notes through the Moodle webpage. Again, yes, thank you for the reminders for the test. Those will be sent out shortly. Again, if there's any questions, feel free to send me an email. There's also questions posted on the website. Again, thank you everyone for participating. It was great to see everyone asking questions, and I hope that this shows you that it doesn't necessarily have to be so algebraic, that in fact in math we can think of stories to explain why something is true. So I hope you enjoyed that introduction to combinatorial proofs and enjoyed the permutation examples and the combinations, and I will see you all tomorrow. Thank you.